all for joining my presentation today. Our work is about Byzantine Lattice agreement in message passing systems. This is a joint work with Vijay Garg. Here's the roadmap of my presentation today. I'll first talk about the motivation behind the problem, and then I'll go over the preliminaries, including models and the problem definition. Then I'll talk about the related work and summarize our results. Our first result is our early stopping algorithm, and second result is an algorithm with logarithmic rounds. And then I'll show you a list of open problems for future work. The primary motivation behind the lattice agreement problem is its application in implementing linearizable update replicated state machines defined by Fedor et al. In this kind of state machine, they only support update and accurate operation, but not update accurate mixed type of operation, and they assume all updates are commutative. By commutative, we mean the order of applying any two updates does not matter. Examples include conflict-free replicated data types and atomic snapshot objects, etc. Another motivation of the lattice agreement is close relationship to atomic snapshot object. Any algorithm, as pointed out by Atiyah et al., any algorithm for lattice agreement can be used to implement ASO and vice versa. So we work on a completely connected message passing system of n processes. We assume there are at most f Byzantine failures, and we assume the system is synchronous. By that we mean there is a known upper bound for message delay, and we measure the time complexity of our algorithm using synchronous rounds. Synchronous rounds is composed of receiving messages to local computation and sending messages. We assume the communication is reliable, which means if a process P send a message to process Q, then Q will eventually receive that message. A joint semi-lattice is a partially ordered set that has a joint for any non-empty finite subset. It can be denoted as a triple. The first element is the set of elements in the lattice. The second one, the less than equal to operator, is the relationship between elements. The third one is the joint operator. Here's an example of a Boolean lattice. The elements of this lattice are all the possible subsets of a universal set ABC, and the less than or equal to order is defined as set inclusion. The joint operator is defined as a set union. A chain in the lattice is defined as a set of elements that are totally ordered. In the example, the elements in the path marked as red form a chain. Height of an element is the size of the longest chain from some minimal element to that element. The height of a lattice is the height of the largest element in the lattice. In the example, the height in the Boolean lattice, the height of an element is just the size of the set, and the height of the lattice is just the height of the largest element. In the Byzantine lattice agreement problem, each process has an input value from some joint semi-lattice, and they must decide on some output also in the lattice, which satisfies the following requirements. The first one is downward validity, which requires that the output of each correct process has to be at least its input value. And upward validity requires that the Byzantine process can introduce at most t values into the decision value of a correct process, where t is the actual number of Byzantine process. It seems like the update validity is trivial because Byzantine guys can propose the largest element in the lattice, and then our argument is in practical applications, we can require that each process can propose, say, in the case of a Boolean lattice, they can only propose a singleton. And also, our algorithm can work for if the joint semi-lattice is infinite. The most important one is comparability, which requires that for any two correct processes, their output should be comparable. Equivalently, all output values of correct process lie on a chain of the lattice. Here's the remaining work and our results. Lattice agreement problem has been studied in crash failure model before, and the best upper bound obtained is order of log f rounds algorithm, and order of log square t early stopping algorithm. Both algorithms have resilience of f less than n. And for the Byzantine Lattice agreement, we are the first paper to propose algorithm for this problem, and we have two primary algorithms. The first one takes order of square root t, which is early stopping, and the second one takes order of log f, and our resilience is f less than over 3, which has been proven to be optimal. In a concurrent work by Di Luna et al., they propose algorithm which takes order of log f-rons and with resilience f less than n over 4. Let's look at our early stopping algorithm. And there's an order of square root t rounds early stopping algorithm for this problem. And we use the Bayesian framework as before, as previous work. Each process sends its current value to all at each round and decides when all received values are comparable with its current value. If it has not decided, then it just updates the value to be the join of all received values. If we only use this basic framework, and in the best case, we can only get an order of a T rounds algorithm because of the Finner chain problem. Because in the worst case, there could be a Finner chain of length T because there are T Byzantine infinities. And in order to get square root t, we introduce two additional ideas. The first one is we use Gradecast to send values. While using Gradecast, we can detect Byzantine process along the way and ignore their values in future rounds. And the second idea is we let each process keep track of a safe lattice, which serves two purposes. The first purpose is to prevent Byzantine guys from sending more than t values into the system. And the second purpose is to combine with Gradecast to obtain the order of square root t rounds guarantee. In the Gradecast algorithm is proposed by Feldman et al. And in this algorithm, there's a leader P which sends a value V, and at the end, each process I delivers a value score pair VI-CI, where CI A is either 0, 1, or 2, which is the confidence score for the leader or for the value. The Gradecast algorithm has the following properties. The first one is if the leader is correct, then all correct process must deliver the same value as sent by the leader, and their confidence score for the leader are all 2. P2 for any two correct process I and J, if their confidence score for the leader are both positive, then their value must be the same. For P3, for any two correct process, their confidence score for the leader has difference at most 1. Property P1 implies that if for some correct process, its confidence score for the leader is at most 1, then the leader must be Byzantine. P2 and P3 implies that if some correct process has confidence score of 2, then for any other correct process, its confidence score must be at least 1. And also all correct nodes will deliver the same value by P2. So to summarize, Byzantine either is called by each correct process or sends consistent value to all correct process. So here's how we modify the original Gradecast algorithm. The primary modification we did is to introduce the safe lattice and use that to filter out invalid values. So each process keeps track of a safe value set SVP which is updated in the main algorithm, and using that, the safe lattice is constructed as the joint closed subsets of X, including this safe value set. And each process also keep track of a bad set B, which stores the Byzantine process detected so far by process P. And process P will ignore messages received from all processes in this bad set. And the rest of the algorithm is same as Gradecast. Here's our main algorithm. Each process has a value V and the bad set B and the safe value set SV. And we assume there's an upper bound f on the number of rounds, which will establish the exact value later. At each round, each process uses Gradecast to send its value to all, and after that, each process would obtain n value score pairs, and a process will update its safe value set to be the set of values that is gradecast with score at least 1, and it also updates its base set to be the set of process which gradecast with score at most 1, and then let you denote the set of values gradecast with score 2. Then the process will check if its current value is comparable with any value in this U set. If that's the case, then it decides on its current value, and after its decision, it will keep executing the algorithm. So at 9.8, it will update its value to be the join of all values received in this U set, which is the set of values with score 2. So for the correctness of the algorithm, upward validity and downward validity are trivial. For comparability, from the decision condition at 9.7, if two processes decide at the same round, they must receive the value of each other, and because the decision condition, then they must be comparable with each other. If they decide on two different rounds, then the process deciding at a later round must have received the value of the process deciding at the previous round and include that into its decision. Then they must be comparable. For the round complexity, we introduced the notion of a terrible process. We say a process is terrible at round R if it's graded with score 2 by at least one correct process in each round before R, and no correct process graded with score 2 at round R. Basically, a terrible process is a Byzantine process that has not been called by all correct process before round R, and is called by all correct process at round R. So clearly there can be at most T terrible process, and our main lemma is suppose there are M terrible process at a certain round, then each process decides in M plus 2 rounds. This lemma is obtained by carefully using our Safe Lattice. And from this lemma, then if we consider the first square root T rounds, because can be at most T terrible process, then within those rounds, there must be a round with at most square root T terrible process. Then starting from that round, then all process must decide in at most T plus 2 rounds, then which means a square root T plus 2 round, which means that the algorithm takes order of square root T rounds in total. Our second result is a logarithmic rounds algorithm. We use a similar high-level framework as previous work. We design a classifier procedure that divides a group into two subgroups and ensure one group dominates the other. And we apply the classifier. By dominate, we mean the values of one group is greater than the value of the other group. Then we apply the classifier within each subgroup recursively. So our main contribution is the introduce and design of a Byzantine tolerant classifier. In this classifier procedure, each process stores a value set, and they also stores a safe value set SVG for each group G. And the Byzantine classifier will divide a group G into two subgroups, the slave subgroup SG and the master subgroup MG. And this classifier has a threshold parameter K, and the classification is done based on the values received at each round and its relationship to K. If we let Fs denote the union of the safe value sets of all correct process for the slave group S, G, then the Byzantine tolerant classifiers satisfy the following requirements. B1, Fs is always a subset of the value set of a master process. B2, the value set of any master process has size greater than K. And B3, the size of Fs is at most K, which means the union of the safe value sets of all correct process for the snake group has at most K values. So suppose we have a such Byzantine classifier, here's how we can solve the problem. So before recursively invoking the classifier, each process gradecasts its value to all, and at the end of this round, each process has at least n minus f values, and by property of gradecast, and Byzantine process can introduce at most f values. So each process can receive at most n values, n possible values in the system. So in order to get an order of log f rounds, we construct the following classification tree, and the threshold parameter is set in a binary way, such that the root classifier, each node of this tree is associated with a classifier procedure, and the root classifier has threshold of n minus f over 2, and the rest are set in a binary way. Then uh, initially all processes are within the same group, and they invoke the root classifier, and based on the result, if they're classified as a snake, they go to the left node. If they're classified as a master, they go to the right node. And our algorithm ensures that at the end of at the leaf level, if two processes are in different groups, different nodes, they must have comparable values. If they are within the same node at the leaf level, then they must have the same value. So here's how we construct a Byzantine tolerant classifier. The first to satisfy the first property B1, we use our basic idea is use set gradecast, which is a variant of the Gradecast algorithm, and the neither p instead of send a single value, it gradecasts a set of distinct values v, and each process delivers a set and assigns a score for each value in the set. If we set gradecast has similar properties as gradecast, suppose each process invokes set gradecast, and let U2 denote the set of values assigned score of 2 by some correct process I. Let U1 denote the set of values assigned score of at least 1 by some correct process J. Then by properties of gradecast, we can conclude that U2 must be a subset of U1. If we look at this example, P1, P2, P3, their current value is a singleton V1, V2, V3. After the set gradecast, suppose the U2 of P1 is V1 and V2, which means V1 and V2 are graded with score of 2 by V1, P1. Then by property of gradecast, those two values must be graded with score at least 1 by any other correct process. So for P2, if it's correct, then its U1 must include V1 and V2. So if by using this property, then we can just construct the safe value set as follows. We use a U2 as the safe value set, and for the master process, we update their values to U1. Then the U2, because U2 will always be a subset of U1, so we can satisfy B1. And to implement to satisfy B2 and B3, the basic idea is instead of like previous work, the classification is done based on the values received at a round. We do the classification based on the safe value sets instead. So here's the code snippet that does the classification step. At line 1 to 2, each process in group G invokes set gradecast to send its current value set. And from line 3 to 7, each process in the system, they will update their safe value set for the snake group and master group. So let U1 denote the set of values gradecast by group G with score grade at least 1, and U2 denote the set of values gradecast by group G with score 2. Then at line 6, a process I will update its safe value set for the snake group to be the union of U1 and its safe value set for current group G. And the safe value set for the master group will be just U2. And because we want to do classification based on the safe value sets, so each process in the system will send the safe value set for the master group, which is U2, to all processes in group G. And from 9.8 to 9.12, each process will uh, receive those values, those sets received from each process in the system. And at 9.10, they will take the union of those sets, and then at 9.11, it will do classification. If the size of that set is greater than k, then it's classified as master, and it updates its value to be U1. Otherwise, it's classified as a slave. It updates its value to U2. So because of the condition at 9.11, the T set is basically the FS. So we know that then for the slave group, the FS has size at most k. So here's some open problems. So the primary one is the lower bound phonetic disagreement problem. So as far as we know, there's no lower bound result for this problem, even in the crash failure model. And our conjecture for this problem is order of log f is the lower bound. All right, thank you.